Good morning, everyone. Today we'll be going through the third assignment of our computer vision course. Now, in the first question, we are asked to capture a 10 seconds video footage using the camera, and we have to use any one of the monochromatic cameras from our OP light. So first, I have written a block of code over here to take a 10 seconds video of our camera. I have slowly moved the camera from left to right to take the video. All the video frames that were captured are stored in the folder video frames. So you can see all the video frames over here. Sorted by the time in on which they are captured. Now moving on, we are asked to pick a region of interest corresponding to an object in the image, and we have to crop out this region of image. And then we have to pick up randomly 10 images from the data set of our entire video frames, and then see if there's a match. So here is the code I have written for that. First of all, I have chosen a random image and then cropped out the region of interest. I have done that manually. Now we can see that this is the region of interest that I have chosen. Uh, I have named it as roi.png. So this is the small object that I've chosen. Mm, Moving on, I performed the pattern matching using both SSD, that is sum of square differences, and normalized correlations. So here is the code for them. I have performed both of these functions, and the functions have been performed on 10 random video frames that were chosen. All these video frames after the pattern was matched have been stored in the respective folders. So if you go to pattern match SSD, you can see an output where the object has been highlighted. So you can see this for multiple of the frames. We can also see the similar. We can also see a similar output for normalized correlation in pattern match and CR. So if you see, you can see that the object has been mapped out. Now moving on to the second question. In the second question, we are asked to implement motion tracking equation, and then we have to select two consecutive frames from the video that we have captured before, and then we have to compute motion functions and estimates. And then using this estimate, we have to perform image registration to realign the frames. So um, here is my code for the second question. The second question can be found in the folder q2, q2.ip1b. So I have chosen two random images from the video frames, and then performed the motion function estimates. Then with the help of this estimate, I have realigned one image on top of the other. So the realigned image can be found in the folder also. So I'll just show it out. So in the Q2 folder, you can see the realigned image as here. Now moving on to the third question. We are asked to plot the optical flow vectors on each frame, and we have been given three sub questions in the same question. That is, we have to treat every previous frame as a reference image, every 10th frame, every 11th frame, and then the every 31st frame. So the code for this can be found in the folder q3 and then q3 ipynb. So this is the code that I have written. First of all, I have initialized certain parameters, and then I have written a function. In function, we can pass an parameter n, where n specifies the nth frame that we're taking. So n is initially set to 1, which means it takes every frame as the reference frame. Um, so I have called this function thrice. Once with n as 1, that is the default value. Once with n as 10, so it takes every 11th frame, and once the n as 30, that is it takes every 31st frame. So all these outputs have been stored in the same folder, that is Q3. In Q3, you can find the optical flow for each case in the folder optical flow. So you can see that this is the flow in the case of every frame. This is the flow for every 10th frame, and this is the flow for every wait okay, and this is the flow for every 30th frame. This is the flow for every 30th frame. Now, moving on to the fourth question. In the fourth question, we are asked to implement a feature-based dropsy detection algorithm from scratch, and then test it on two differently looking objects. So here is the code that I've implemented for a feature-based object detection from scratch. It's in the folder Q4 in q4.ipynb. And then this is the function that I've written, that's object detection. It takes the image, the template, and the output file as input. And then for the sake of testing this algorithm, I have taken the picture of I've taken the picture of a book. So the picture can be found over here. This is the picture that I've taken. And then from this, I have chosen two objects of choice. That is, I have chosen the blue flower and I've also chosen the red flower. I have performed feature-based object detection, and the object detected can be found in the folder object detected. So you can see how the blue flower was identified in this region and how the red flower was identified in the next region. So over here. So since the algorithm I have written does this for only finds only one object, we can see that only one instance of the flower has been found. Now moving on to the fifth question, we are asked to implement real-time phase detection. Um, real-time phase detection, I have done this with the help of HAR features and performed the experiment on both real-time and as well as a recorded video. So mm, the code can be found in the folder Q5 in q5.ipynb. You can see that here I have given the option for both using a live video or using a captured video. So as an example, I have used a captured video, but you can also use a live video. The From the video, each frame is taken one at a time, and then the faces are detected on the frame. The frames are then stored in the folder output frames. Now, for ease of understanding, I have again recompiled the output frames into a video and converted it into an MP4 format, so it can be easily verified. So if we go to the Q5 folder, we can see the output frames in this folder, where you can see how the faces have been detected, frame by frame. And then the final video can also be found in the same folder, that's output video. And you can see how the faces are being found. Okay, so moving on to the sixth question, that is the final question of this assignment. In the sixth question, we are asked to fix a marker on a wall or on a flat surface, and then we are supposed to take the picture from a distance d while keeping the camera stationary, and then we are slowly supposed to translate the camera by 2 units towards the left or right with the axis parallel to the ground and capture one more image. Now we are supposed to use the disparity based depth estimation to find the d. So I have done exactly the same in the code q6.ipynb. First of all, I've taken the picture of the marker. As you can see over here, I've placed the marker on the ground. I've taken a picture at a distance of 1 meter from the t, that is t equal to 1 meter. Um, Sorry, d equal to 1 meter. And then I have slowly translated the camera by I think it was 1.6 centimeters to the right, and then taken one more image. So these are the two images that we can see. These were taken using the um, monochromatic left camera on OGD light. Next, I have this is the function that I have written for calculating the disparity. Over here, I have given block size as an optional parameter. So it is block size is set to 5, but you can also change the value. So you can see that on calculating disparity, this is what we get for a block size of 5, and this is the disparity we get on a block size of 25. Mm, now that we have the disparity map, I have calculated the depth map. So we know that depth, from the equation, we know that depth is um, the baseline, which is d in the question, times focal length divided by the disparity. So this is the formula. I have used this to calculate the depth map, and this is the depth map I have got. And then on trying to find the depth of the marker, we get it to be approximately 47 centimeter, which is like half a meter. And our camera was placed at like 50 centimeter from the mat from the marker. So I gave an error of around 3 centimeter. So that's the end of assignment 3 for computer vision course. Thank you.